Welcome back to In Depth With. I'm Richard Price, your host and founder of academia.edu, and I'm super excited to dig into another fascinating piece of research, so thanks for joining me today. Remember, what I'll be sharing is a neutral presentation of a paper's ideas. I'm not indoors the method or conclusions, just giving you insights, your own reflection. Today's featured paper is called Calculation of Maximum Coronary Dilation Pressure Using IVUS Analysis and Material Mechanics, and it's authored by Dr. Karim Hnid. Honestly, this is an example of academic research that's both incredibly technical and really relevant when it comes to medical safety. If you or anyone you know has ever encountered terms like angioplasty, stenting, or even more intimidating, intravascular ultrasound, this episode might just demystify a few things. So, at its core, Dr. Hnid's paper is asking, how can doctors figure out the safest possible pressure when using a balloon to open a blocked coronary artery, specifically during an angioplasty? The main issue here is avoiding something every doctor dreads, accidentally rupturing the wall of a patient's artery. Too much pressure, and you might cause a tear that leads to bleeding or blocks blood flow entirely. Scary stuff, right? But not enough pressure, and well, you're not treating the blockage effectively. So, how do clinicians walk that fine line? According to Dr. Hnid, traditional methods don't always account for the unique properties of a patient's artery or the specific makeup of the plaque inside it. This is where IVUS, or intravascular ultrasound, comes in. IVUS actually allows doctors to see a cross-sectional image inside the artery so they can measure things like the thickness of the plaque and the size of the vessel, and even figure out the composition of what's causing the blockage. Is it mostly fatty, fibrous, calcified? Every composition has different mechanical properties. Now, I'm going to walk you through the paper's main idea, but I'm doing it neutrally. I'm not saying this approach is perfect, just sharing the research so you can decide what you think for yourself. So, Dr. Hnid proposes that by combining the measurements from IVUS with principles from material mechanics, yes, that's physics, you can estimate the maximum pressure you should ever use to inflate that balloon. This is kind of like figuring out how hard you can pressurize a soda can before it pops. Each plaque type in the artery wall has its own rupture stress, the pressure at which it'll fail. The trick is calculating a combined rupture stress that reflects the real mix of soft and hard material in that person's plaque. The method goes like this. First, the physician takes IVUS measurements, so they'll get the inner artery radius, the plaque thickness, and determine what percent of the plaque is made of lipid, fibrous, or calcified material. Then, using mechanical properties from prior research, they calculate an average rupture stress based on the mix. Next, here's the clever part. They apply a version of Laplace's law, which is usually something engineers use when thinking about pipes or balloons, and adapt it to the shape and structure of an artery. You end up with a mathematical formula, right? It lets you punch in the IVUS measured numbers and theoretically get the optimal, safest pressure for balloon inflation. No guesswork. In fact, Dr. Hnid even walks readers through a numerical example, showing how these numbers can be crunched step by step, converting everything so you end up with an answer in something like atmospheres of pressure. Just a quick pause here. I once saw an episode of some old medical drama where they used a bike pump and a garden hose to demonstrate angioplasty, which, thinking about it, is actually kind of hilarious. But anyway, that's not real life, but it does make you appreciate how much precision and math go into these procedures. And again, my job isn't to say whether Dr. Hnid's version is the answer, just that it's one possible approach academics are developing. For you as a listener, maybe you're thinking, okay, why should I care? Well, if you or your loved one ever needs an angioplasty, you want to know the science is there to minimize risks. This kind of research, even if it's early days, moves medicine towards more personalized, data-driven care. Instead of relying on generic safety margins, clinicians could, someday, tailor the procedure to the exact condition of a patient's arteries. But, important but, as always with academic work, these are models, not absolute truths. Real life. Messier, the method needs real-world validation. Doctors always need to use judgment, and new research might refine or even overturn these equations over time. So that's all for today's discussion on Dr. Karim Hnid's paper about coronary dilation pressure, IVUS, and the magic of mechanical physics applied to medicine. Thanks for listening to In Depth with Academia. I'm Richard Price, and I hope this sparks a new appreciation for the intersection of math, engineering, and medicine. Without ever promising you definitive answers, keep questioning, keep reading, and I'll see you next time.